Good afternoon, or good morning, good evening, everybody. Welcome back to the developer track of CloudStack Collaboration Conference. Our first speaker today on this track is Rohit. Rohit's going to be talking about the next generation virtual router. Over to you, Rohit.
Thank you, Giles, and thank you everyone for coming to my talk. In this talk, we'll talk about the next gen virtual router. I'm Rohit Yadav, principal engineer at ShapeBlue. I've been leading the engineering function at ShapeBlue. I live in Gurgaon and I've been working for CloudStack for more than 9 years now. In my free time these days, I'm maintaining the Raspberry Pi ARM64 port for CloudStack, and I love CAT and programming. So the agenda for today's talk is to go through the problem and pain points of the current virtual router and the components around that. Just to recap certain things which were discussed in the past, look into some ideas, experiments, maybe demos, and then if we have time, go through some Q&A. So I've already given 2 talks in the past, one in 2018 and the last one in 2019 around virtual routers and the improvements around that. So I think the way I would like the audience to sort of interpret this talk is that it's all about the destination. Sorry, it's all about the journey, not the destination. So a lot of things we will discuss in today's talk might not really happen in CloudStack because a lot of them are still at the idea/design stage. What are the problems and pain points of virtual router? So I think first and foremost, this has been going on for years that the code base is difficult to maintain. It's difficult to develop and test. Upgrades are an issue. We have made a lot of progress since past couple of versions, but upgrade is still an issue for a lot of users. There's lack of an API. A lot of the code base is nothing but a bunch of scripts and shell scripts, Python scripts, and it's kind of written in a very hacky way where people would, when they implement a feature that generally requires CloudStack management server or agent to SSH into the host and then execute those scripts. There's also some performance issues. So for example, if you have 10,000 firewall rules, it can take a lot of time to process them. So there's a lot of implementation, script, upgrade, and code-based related issues. While we talk about virtual router, we also need to look at not just the virtual router, but the systemvm template, because the lifecycle and management directly affects the virtual router. And we have a non-standard sort of approach of creating our own sort of distribution of Linux, which we call systemvm template based on Debian. And there's a lot of issues around patching and upgrading it, creating it, and whatnot. And frequently with all past releases of CloudStack, at least the recent ones, they have all required installation, registration, and upgrade of those templates. So basically, what do we want to solve for? We want to solve for the development and maintainability of the VR code base. We want to solve for how do we test that specific virtual router code base. How can we upgrade virtual router with minimum impact if possible? Also look at the performance, security, and robustness of that code base. Finally, currently, the scripts are all executed through SSH. There's no specific client support through API or RPC. So maybe that's another area or aspect we want to look for. Just to recap, the systemvm and the virtual router lifecycle have a lot of similarities. It starts with building the template in the first place, for which we currently use Packer. Then we have to host these templates somewhere, either on community servers or on ShapeBlue S3 and etc. Then when somebody installs CloudStack, you have to install or seed those templates. And if somebody is upgrading CloudStack, they have to register the template. For that, the information is spread through documentation, some scripts. And once you get past the sort of initial steps, then it comes to lifecycle. Lifecycle of a system VM and a VR involves creating that disk of their virtual machine, configuring the NICs in case of different hypervisor, either a link local IP or NIC, or a private/control NIC is used. In terms of initial configuration, we pass a string, a sort of magic string called command line, which we'll get to in a moment. And then patching, which means setting up the right scripts, the code base, the software packages is done through a systemvm.iso file. The focus of this talk should be about RPC and the stuff I've highlighted in the green. which is programming of the virtual router and how do we improve that. For virtual router, that will be SSH and databags currently, which uses JSON and XML payloads. But we have to do a bit of yak shaving, which means we have to look into system vm template as whole before we think about the virtual router. So the purpose of this slide is just to show that this is how we program virtual router, and this is not acceptable. So we have to start with yak shaving the system vm template. So let's do that first. Just to recap, this is generally how system VMs are patched. It starts with the magic string command line, which we fed to the VM, which boots off the system VM template. We attach a systemvm.iso file, which then uses a script called cloudly-config to determine various parameters from the command line string and patch and create that system VM. Inside the systemvm.iso file contains an agent.zip file, which is just for CPVM and SSVM. These are Java binaries or Java jars. The cloud script tarball is what is the sort of VR code base. In addition, we can have an authorized key file, which is the management server's public SSH key. And for every hypervisor, the way patching works is kind of non-standard. It's kind of unique per hypervisor. So let's look into some ideas and experiment. We know what is required. We also know what we're solving for. To start with system template improvements, we have, since the last talk, we have made some improvements, and those things are now confirmed in the 4.16 release, which was voted. The vote has passed, I think, yesterday. So historically, system templates were built and hosted on a separate server, and users were always required to sort of install, seed, and upgrade, or register those templates prior to an install or an upgrade. But now those templates are bundled into the CloudStack management package. Specifically, the no Redis package or the no Redis build type will include or bundle those templates, which means that now we have an auto seed or auto install or auto upgrade logic. So people don't have to think about those steps, which are normally documented in the release notes or in the install documentation. So now people can simply do an apt-get update and upgrade or a yum update to upgrade CloudStack. They don't have to worry about the steps, the manual steps that are required to set up your system in template. This sort of feature or this sort of enhancement also makes CloudStack turnkey, because if you think about it, the system in template is not an optional component of CloudStack. It's pretty much required if you want to do anything with virtual machines, specifically with the templates and ISO and whatnot. So by bundling the part of the software, which was hosted separately within the deb and rpm packages, it kind of makes CloudStack turnkey. In addition, we have reduced the dependency for CKS. CKS used to have a separate template, but now the same system in template can also be used for CKS host. So here's an idea. We have made some improvement, which is in 4.16. That's great, but let's think of some ideas that we can explore. We just looked into the systemvm patching process, and the systemvm.iso file exists, but the question is, do we really need it? What if you remember from 2 slides ago, it contained an SSH public key, which we can suppose pass to the systemvm in the command line string itself. Furthermore, when the management server starts, the first thing it tries to do is inject the keys in that ISO file, which won't be needed. The other thing is we did some tests just to check, if you have the command line string itself sent, which sets up the NICs, can't you use the dhcp or SSH mechanisms to patch the system payload, depending on whether it's a virtual router or not? And we found promising results. So it looks like we might deprecate and remove the systemvm.iso file in future. And that's great, because that's like one less dependency, which requires secondary storage, especially for hypervisors such as VMware. Okay, maybe that idea sounds promising, maybe doable. What about looking into the patching process itself? We use this command line string, and this command line string is sent to the systemvm, let's say, booting process, and it's not standard. It's specific to a specific hypervisor. So maybe it's worth thinking, can we explore maybe use of Cloud Init? If we deprecate systemvm.iso, can't we use the config drive feature in CloudStack to automate that? Furthermore, by moving to a standard process, user data or a config drive based process would make it even better for people to use systemvm templates, because that's one less custom thing to sort of support. Further, because we are thinking to deprecate systemvm.iso, it's like you're replacing that ISO with a config drive ISO. And furthermore, because we can move to a standard process, you don't need hypervisor-specific tools installed in the systemvm in order to patch the template. There's another idea, which is we can explore IPv6. We know the MAC address of various NICs, and we know the link, the L2 networks on which the systemvms are sort of created. Can we maybe explore that idea of using IPv6 link local address to directly talk, to let one of the parties, either the KVM agent or the management server, sort of talk to the VR directly? The third idea is maybe can we have smaller templates? The current template is about 500 megs in size. And if you're bundling 3 of them for 3 hypervisors within the packages, that's like at least a gigabyte of additional package size that we have expanded. So for that, I explored a couple of ideas with my team involving Wei, Pearl, and Alex. And we looked into various options that we have on board throughout the ideas that we'll present in this talk. The first thing we looked at was Alpine-based systemvm template, because if you go and search for various Linux distros which are meant for small routers, firewalls, Alpine kind of comes up at the top. Alpine is already used for creating Docker templates. So as a sort of quick demo, I can show you the Alpine-based systemvm template. And before I show you the demo, let me show you why we want to explore that. So we want to have smaller templates. That means the size of the template has to be small, and it has to be faster build. The Packer-based build can take anywhere from 15 minutes to 30 minutes to build. And because it kind of boots a real VM to sort of create that VM template. Instead, the demo that I'll just show you very quickly, what it does is it uses QEMU NBD. Essentially, it uses QEMU NBD and Chroot to sort of create a template. It takes usually less than 60 seconds. So let me just do a sudo time and bash on this. And this whole process will take anywhere from 30 seconds to I think 60 seconds. The quickest one I got was probably 10 seconds. So if something like this works, then we can think of building the system template as we build CloudStack using Maven, instead of the current process, which basically tries to download the template off internet. If every template is 500 megs in size, that means you're downloading at least 1.5 gigabytes of sort of total data payload before you sort of create a template. So while I was just speaking, it has already installed the Linux kernel, and it is installing various utilities. These are all the tools that you require to build a systemvm template, like the Java runtime environment, Apache IP Route 2 for firewall, OpenSSH for the SSH server, HA proxy, Python, all those utilities that are required to build a systemvm template. So it has completed the systemvm template build in about a minute. So that's not bad. Furthermore, it can take anywhere from 1 minute, another 1 minute to convert the QCOW2, the image file, to various hypervisors. In this case, it has started converting the template from QCOW2 to an optimized, compacted QCOW2. Now we are, I think, trying to fix Zen server. So Zen server is done, and now it is trying to build VMware. So I think within a matter of 2 minutes, or within 2 minutes, we can build a systemvm template. So we can think of an optimized template, and this is just 100 megs. So if we compress the Zen server VST, so that will still be like 300 megs in total for the 3 hypervisors, compared to 1.5 GBs that the current sort of build system takes. That is just one example of looking into that. However, this experiment didn't yield much result because there are specific Debian dependencies that the current VR code base uses. So, but nonetheless, I think this experiment is still useful. Another example can be that there is one image format that works on all hypervisors, and that is ISO, right? If you have an ISO, you can boot on all the hypervisors. So why do you need to have 3 different image builds, QCOW2, OV, and VSTs? Why not just have one ISO and do that? And this is an example. I won't go into the build steps, but it uses similar kind of concepts where it creates a directory, then Chroots into that, and then it installs all the packages. This again takes anywhere from 1 to 2 minutes, and you get a sort of an ISO. So it's like one ISO. Again, this is a Debian-based custom live ISO, where the Linux kernel side of boots off that, and then the idea there is that you have this ISO which can boot off the virtual machine as sort of your read-only root FS, and then you have a data disk for persistence. So any packages, script, file, tool, the VR agent that you installs on the data disk, not the root ISO. So that might be an interesting feature or an idea also that's worth exploring. The third thing we looked into was let's optimize the current build system we have with Packer. And for that, we looked into all the packages with various sizes. Surprisingly, we found the Linux image kernel, the default one that gets installed on the systemvm template, consumes anywhere from 200 to 300 megs in space. And I looked into why that is. And the reason was that because that's an unoptimized Linux kernel. It has drivers for webcams, printers, audio, and all those things that you don't require for a Linux kernel running your virtual router. So we tried to see, can we use the Linux cloud kernel, which is an optimized version, which doesn't have those modules. But surprisingly, that didn't work out of the box on VMware. So we have to drop that optimization. So, okay, we have done with some yak shaving. What else can we do for systemvm template improvement? So I suppose we can revisit the patching and upgrading process for systemvm template. So the idea is that irrespective of different versions of CloudStack or different versions of systemvm template, there's one thing which is unique and which we almost guarantee will exist in all those system VMs, which is SSH ability. You can SSH into a system VM even if you change different versions of CloudStack. And then the idea is, can you introduce some kind of live patching process, which is you upgrade CloudStack and then instead of destroying your existing VR, can you simply live patch it without actually causing some without requiring the user to restart and destroy the old VRs. So with that, we thought, okay, let's explore our options. The first option we explored was somebody advised, why don't you look into Docker? The problem with Docker is we are limited with the number of cores, that is usually one for the VR, and we are limited by the RAM, which is usually 256 MB of RAM. That's for the default router offering. So we looked into why can't we just have file system isolation, not the whole container isolation. So we started looking into overlay-fs. And the general idea that's still yet to be sort of developed is let's have a read-only root file system with just the kernel and some utilities. If you think about the core services that the VR offers, the core services like your NAT, your firewall, your DHCP, DNS, all those things may not require user space utilities. Maybe DHCP requires that, but other things like connection tracking, firewall, NAT, those things don't. So they are part of the Linux kernel themselves. And the user space utilities like IP tables, NF table, IP route 2, those packages can change, but the underlying Linux kernel can continue to function. So with that, we thought, okay, let's explore the idea of overlay-fs, where there's a concept of a lower and upper directory, where the lower directory in this case can be a read-only root fs. And the idea is that you would create a folder like /router in which you have different versions of CloudStack in which you can put the router-specific code base. This is how Snap also works. There's more information on the Debian wiki on how we can have read-only root. So that's also an interesting idea worth exploring. What else? Maybe there's another way if we can't use overlay-fs, because we saw there are some issues with using that. Maybe just install the Linux kernel and utilities. I keep the template really small and tight, and instead of pre-installing all the dependencies like HA proxy and Apache and strongswan and all those dependencies, why can't we install them during patch time, which means having a fatter systemvm.iso which has those packages, maybe the dev packages. And that's not a new idea. We have been sort of using that sort of approach with CKS, where the CKS template doesn't have Kubernetes version-specific binaries installed. They are bundled through a fatter CKS ISO file. So we may look into exploring that. Or there could be another option, which is the systemvm template does have a static directory or ability to serve static files. So why can't we have a Debian-based repository, assuming the systemvm template is Debian-based, which can have those packages in. So between different versions, all the VR needs to do, or the VR upgrade or patching system needs to do, is simply repoint and update the repository and run like an update or upgrade to just update and upgrade the user space dependencies. Okay, what about another idea? If even those may not sort of work or they don't sound really good, which is how about we just have a standalone VR agent, right? So the idea is that it's a single binary or a module that can replace most of the non-core services. The non-core services are DHCP and DNS server, password server, your VRRP, health checks, monitoring, metadata server, and they all can be served by a single binary, right? A single process can handle all of that, and this is a strategy used by a lot of Golang based projects where a single sort of binary will act as all of those services. And there are existing libraries available using which you can sort of create your DHCP DNS server, all of those things that I mentioned. And the core services can be continued to be provided by the kernel, like your NIC and routing, your firewall, all those things. And we have some ideas in the pipeline that we're thinking of, making the existing features to have a framework. Like instead of having VPN, which is currently provided by just strongswan, why can't we use a VPN framework where there are other user space utilities that a user can specify, like strongswan, wireguard, OpenVPN. So those are probably good ideas worth exploring. This is just a slide from a previous talk to basically say how we define a core versus non-core service. Core services are being those that causes a network downtime. So every time let's say if there is a user space utility like the password server, Apache server, you can pretty much upgrade those packages, restart. The failure or the downtime won't be affected. But if you restart for some reason the network, the firewall, and those things, that can cause downtime for user games. Okay, that's basically to think about systemvm template. But there's another idea, which is why not just look into off-the-shelf router distribution? Why not just pick one that kind of already exists out there? And I looked into that, and we sort of concluded that there are many licensing issues. There are issues around longevity of the project. So, for example, top three, without sort of getting the specific names, they all, when you go to the website, they are all sort of commercially backed projects that just happen to be open source. There's no real community around that. And OpenWRT, which a lot of people may not have high, let's say, thoughts about, that is really good. I mean, I thought from a community point of view, the first three were giving payment plans, and the fourth one, OpenWRT, was saying go come and donate. And on the website, I think this is the only one where it says it's by the community and for the community, with over 18,000 GitHub stars and a very high commit activity. The project has been around for, I think, more than 17 years, as much as, I mean, it's as old as Linux itself is. So from that point of view, OpenWRT may be a good idea. So before I actually jump into the sort of screens, other slides, I'll just quickly demo what OpenWRT is. So what I've done at my home is I've installed OpenWRT on a Raspberry Pi just to test out, what does it feel to have an off-the-shelf router, just to really sort of, dog food this before this thing. So I'll quickly show. The one thing I really like is they have an API system that's backed by Lua. They have a UI, it's called Lucy, where I can see a lot of statistics. I can look into the firewall. I can look into the routing table. That's all sort of GUI based. So I think that might be an interesting sort of feature to have something like OpenWRT, which has a nice little UI, and you can see real-time graphs. You can see connection sort of being tracked, and of course, they have. I mean, one thing I really like about OpenWRT is, much like other Linux distributions, it has OPKJ, which is like app.yum. It's like a package manager with which you can sort of search and install packages. So based on what I've found, I think most of the packages are available in OpenWRT, so we can have that. And they have really nice network support. So you can have multiple NICs and zones. You can do static routing, DNS, DHCP. And the good thing is they already have an API, a sort of dbus-based API or a Lua-based API. So the integration of something like OpenWRT may be promising, maybe even feasible. So let's go back to our slide. Okay, we have some option, but I would still like to explore what we currently have, which is the only, I think, the only feature I couldn't think of, which we will have to work on OpenRT, is VPC support, because VPC is more than your typical CPE use case. So just to recap very quickly, the current implementation uses a VR deployer class. It has, this is what kind of SSHs to your virtual router and executes some scripts. And generally, it starts with copying a JSON or a XML file and executing an update, script. For data model, we use JSON and a combination of XML and data backs. This is really messy. It's like everyone has their own sort of implementation. There's no standard way of programming the router. We don't have a proper database. We use just JSON files in the etc CloudStack directory. For communication, we use HCP and SSH, and we have sort of logs. So it's a highly simplified version of the workflow we got right now, which is step 1, copy the JSON file. Step 2, execute a script, which will read the sort of JSON data bag, and then it will process and return an answer to CloudStack. So we have to kind of see, how we can like optimize and think of all those aspects of, let's say, if we were to introduce a new VR agent. And when we do that, we have to be aware of certain VR limitations, specifically that it has a limited RAM and CPU in the sort of default offering, and it patches a custom sort of hypervisor specific way using command line string. And it kind of uses SSH as an RPC mechanism. So if you think about this, going back to this slide, the RPC is something like, there's a data bag which gets HCP'd, and then you call a script. It's kind of hacky, but that's kind of a SSH-based RPC. In terms of agent ideas, the first thing is, what do you write this thing in? Because now we are thinking of a new sort of agent from the scratch. We can go with Python 3, but then you have still the same kind of an issue, which is there are multiple files, not a standalone thing. With Go, you get the standalone sort of agent, but then somebody has to compile that agent. That means it can't be patched on runtime, which means if there's a production issue, you need to patch something, you have to build the binary first before you go and use that agent. However, there is a way, which is you can run Go as a script, and you can Google about that. The third thing is an interesting idea that was inspired from OpenWRT, which is Lua. Lua is much like Python, but it is highly optimized, runs at almost sea level, and LuaJIT is like you can think of Lua on steroids. And the fourth option is, of course, shell scripts. Just have a shell script that manages everything. So that shell script idea may make sense if, let's say, we were to switch from Debian to OpenWRT as a Linux distribution, where the shell script will, sort of create like a wrapper on top of UCI or Lucy, which are the current API mechanisms. In terms of data model, we can't use the same JSON and the XML approach data bags that we have right now. I'm thinking the simplest thing is to have plain old Java objects. That means there is a Java class or object to serialize into JSON and deserialize to another language that that the VR agent is written in. For that, we do have IDLs, or the interface descriptor languages like protobuf, Thrift, and Avro, where there'll be a compiler. So you sort of define the interface, and it will generate the client and server stuff for you. There's also an option of sort of doing something of our own, but it makes sense to use something like protobuf or gRPC, which is pretty standard or widely used these days. In terms of database or sort of VR's own view of the world, we have JSON files right now, but we can look into SQLite. So SQLite as a way of having a small database on the virtual router. Or we can simply serialize and save the protobuf objects or the ideal objects at some folder. In terms of API or RPC, this is where things sort of get interesting, and I have a few quick demos to kind of show you. Is SSH. I mean, use the plain old SSH or a tunnel to to let the KVM agent or CloudStack to talk to the agent. We can have an HTTP server. This was a suggestion from my colleague Wei, which can run from CA framework issued certificate and listens on a custom TCP port, which is only accessible through either the link local IP or maybe a new private NIC just for programming purpose. Then we can also have Unix domain sockets, and these are the two examples I'll just show you very quickly. So these are two options, Unix domain sockets and named pipe, to be used as an IPC mechanism. That means you SSH into the VR, so you get the security of SSH, but then some process or tooling can use those IPC mechanism to talk to the VR agent. So let me just begin by showing you two sort of examples. So let's look at the named pipe example very quickly. So the idea is very simple. So what I've done here is, let me remove the bus. So what I've done here is I've got a simple Python file. What it will do is it will create a named pipe. So named pipe is like this. So let's say when I do something like this, So this is a pipe, and this is an unnamed pipe. What it does is it kind of takes in data from one process, passes to the another process. So named pipe are unidirectional, but they are great. I mean, let me show you the demo. So think in this way. So if I say Python and busreader.py and I create another sort of terminal, if I sort of cat anything, so let's say I need to SSH into the host first and get into the VR demos directory, right? And maybe go to the name part directory, right? So here, if I write anything and just cat to router bus, you can see the other process can read. So this actually applies if you HCP something, that will also work. So for example, let's say I got this payload.json file, and if I HCP this payload.json file, let me first find the path so that I can do that. I can simply HCP the file itself and say I want to go to the address. So think of this as a router proxy, somebody trying to get inside the VR and simply HCPing the payload itself. So I think I can try to do that from my other system. So let me copy this, exec, and instead of payload file, doesn't matter what that payload file is. So instead of that, we can just, for demo purpose, send any file. So I'll just send this, and it still doesn't work because I've put in the wrong IP address, right? So notice I've sent a file, simply HCP'd the file, and that file can be read by a process, sort of a running process. So let me try to SSH again, and go to the lab, VR demos, go to main pipes, and try this thing again. So the idea is that I HCP the JSON file, and unidirectionally it can be read by a VR agent, which kind of runs inside the VR. So that's the idea of named pipe. Unix domain sockets kind of work in a sort of similar way, where they'll be bidirectional. So the problem with the named pipe or Linux message queue is that they are unidirectional. There's no way to sort of get a response back. So in the next sort of demo, let me just close this, go to the other thing. Let's look into the Unix socket example also. So the whole idea here is that, let me remove the sock file, is that you got a server. So let's say you got a server running. Now what this server will do is, let's go to the Unix socket. What the server will do is will create the sock file, right? So it's like a file to which another process in HCP maybe can rewrite stuff into. And I've got a client.py just to demonstrate this. So what this client.py is going to do is to read the sock and try to send some data, like a realistic sort of JSON payload. So let's try and run that. So say Python client.py. Notice what happened. Client kind of sent this JSON. To think of having a Unix socket-based server that listens on a Unix domain socket file, which is inside the VR, right? And this client can be a CLI, or it can be the VR agent, or sorry, it can be the KVM agent or the management server trying to send the VR agent some command, like go and add a nick. In this case, maybe add a host name or a DHCP entry. And then you can get a response. So this can help us create a command line, a command answer pattern for RPC, just like we have it between the management server and the KVM host. Now let me demonstrate another example where I'll use another system. So Ripper was 1.100 and Spectre is basically my own laptop. And what I can show you is a router proxy, right? So it's like two different systems, and can they forward sockets? So SSH allows you to create a tunnel where sort of a remote socket, so like this sort of socket, will be forwarded from the socket which is in another system. In this case, think of this as forwarding the remote socket which is inside the VR to my host, which can be the hypervisor host, or it can be the management server in case of, let's say, VMware. So what I'll do is I'll first run the router proxy. So you can see the proxy is being running there, and I'll split the screen maybe vertically this time. And what I'll do is I'll just run the client.py again. So to client.py, it will get this socket bus somehow, right? It will be automatically created by this tunnel, and client doesn't know where this agent is. What client will do is simply read and send data to the router bus. So let's do that. So if I run this, it's the same thing, right? So notice what has happened. As soon as the client sent this payload, this payload was sent through the SSH tunnel. So you see on the left side where it says, something is trying to forward and talk to the client. So this is an example of the Unix socket, the domain socket being forwarded from the VR agent, from the virtual router itself to a hypervisor host or the management server itself. So you get the sort of benefit of security and the sort of backward compatibility. So you don't have to change a lot of stuff. Okay, back to our slides. And I'll revisit whatever demos we just saw in a moment. So that's basically for security, right? If you have a HTTP-based server running inside the VR, we can use the CS framework, or we can use good old SSH to create a tunnel and forward things between the VR to the hypervisor host or the management server. Okay, what else can we think of the VR? If it is a bunch of scripts that are being copied to a specific directory, then we can look into in-place upgrades, or we can look into overlayFS, where you can toggle between multiple versions of VR agent in the VR. There's another option, which is the management server can live patch the VR, so you don't have to reboot system VMs. It basically just works. And you can have pre and post upgrade hooks to basically check whether live patching actually worked and notify the user whether live patching worked for some VMs, or that is VRs, or not. One thing again to iterate is we assume and we know for sure that SSH will work even when you sort of upgrade between system VMs. So SSH is one thing we kind of count on, that let's say since 4.2 or 4.5 version, we know SSH can work. So that is our tool to exploit to explore live patching. So just to reiterate, how does a VR agent can talk to MS agents, the management server or the KVM agent? So it's kind of different for different hypervisors. Like in case of VMware, the management server already talks to the VR directly using the private or control NIC on the VR. In case of KVM and Zen server or XCP, we have a link local IP concept. That means you have to first SSH into the hypervisor host, and through that you can get into the VR. And the two examples we saw, the named pipe example and the Unix domain socket sort of prototype demo, can be used in both these options. However, if somehow all the hypervisors can be moved to a standard, which is that all hypervisors will require a private or management NIC on the VR, then we don't need to explore those hacks. However, the trade-off is that Zen server and KVM environments, like users, will have to add some kind of a pod IP range, some kind of an IP range, which is used to sort of allocate that control network on the VR. Otherwise, we can explore the sort of demos that I've showed today, which is management server can talk to the VR via proxy or directly. So in case of VMware, it's not needed. You can directly forward the Unix socket, for example, the Unix domain socket from the VR to the management server host itself. And in case of KVM and Zen server, you can do it through the hypervisor host plugin or the agent. So it's like replacing the router proxy by having a forwarded tunnel that exists on the hypervisor host. So that was the experiment we just saw, named pipe. Here, the idea is that named pipe can use the serialized object, in this case, the protobuf or JSON. The cons is both with the named pipe and the Linux queue features are that these two IPC mechanisms are unidirectional. Surprisingly, these are not implemented unidirectionally for other operating systems. It is possible to have bidirectional pipes, but that's the sort of limitation in Linux. So that's kind of out of question. We can't use it. The other option is Unix sockets. And the great thing about Unix socket is, let's just quickly look into the implementation of that. So if we go to this, go to the VR demos, go to Unix sockets, the implementation is pretty straightforward. All you do is you say listen to the Unix socket, and this can be simply replaced by TCP or something else. So the server logic remains the same, only the declaration whether the protocol is Unix domain socket or it's a TCP, INET4 based service, that can be changed. So the Unix domain socket approach makes it easy, kind of future-proofs the VR agent in case, let's say in future, we decide to listen on TCP or TLS. So that might be an interesting idea worth exploring. So in sort of a very simplified future, the future might look something like this. There is a library or some sort of a code base which is hypervisor agnostic, which allows you to have an RPC mechanism much like you have the command and answer pattern for KVM agents in CloudStack. And with that, you RPC using either HCP or SSH tunnels or Unix forwarding or TCP TLS ports, so one of those mechanisms. And then there is a server. So the VR agent is essentially a server which runs as a daemon and can process requests. Basically, the management server or the KVM agent becomes the client, and they send the command to be interpreted and executed by the VR agent. So this is, in summary, what possible future can look like. A VR agent, a daemon that is written in either Python, Go, or Lua, or maybe something else. For data model, we use something like protobuf or plain old Java object serialized into JSON. For database, we can again use SQLite or protobuf. And for RPC, we have the SSH-based tunnels to tunnel and forward Unix domain sockets, or just have a TLS, CA framework-enabled TLS server. In addition, because if we use an RPC mechanism like protobuf, we can also have a new sort of VR CLI. So think of people having a dedicated UI or CLI, so essentially clients for the VR. The virtual router itself can be spinned off as a sub-project of CloudStack. And the workflow will largely look like this. Management server or the KVM agent sends a command through an RPC mechanism to the VR agent, which processes and sends back an answer. So it's a pretty straightforward, I think, model or design we got. That's pretty much for this talk. Thank you for listening, and let's do some Q&A if you have any questions.
There's a few questions, Rohit. I'll just dive straight into them. So Christian's asked, will there be an option in the next gen VR to run in a bridge mode? Very often we need the public IP direct on a VM without natting it.
I suppose that's for that you should use shared network, right? So the VR agent is actually about not about implementing the network model or topology. It is about managing the VR itself. So if your use case is to have no natting, then I suppose the kind of network model you're looking for is a shared network, because there VMs directly get IP addresses, public IP addresses.
Cool. And actually, I'm Vladdy's question, which has come up next, I'm going to sort of elaborate on that a bit. Vladdy's asked, what do you think is the best option? And actually, I really like your talk in that you just explained your thought process and all of the options, but let's try and pin you down now, okay? Out of all of these things, right, what would that next gen VR look like if you did it tomorrow?
I think from what I understand right now, I'm really liking Lua for now, because one issue with VR is, let's say if you create a simple hello world program that just says hello and loops infinitely, the Python process consumes a lot of memory. Go is sort of behind and Lua is kind of top. Writing Lua is good. However, Go has that sort of benefit of creating a standalone, like a single binary you can HCP. So patching process will be much easier if you have a VR that is Go based. So the thing is, we want to do this in Apache way. That means I might have a preference, but the correct thing to do is to write a design document as a sort of next step after this talk is done, to capture all the thoughts, come up with a possible solution, discuss with my team, especially Wei, Pearl, and Alex, who are, by the way, credits to them. These are not just all my ideas, but it's being discussed as a group. So the next step is to propose that to the community, and I'm sure people will have their sort of opinions on what should be used and what not. If you ask me, because you've sort of pinned me down, Jazz, I think I'll say go with Golang, use protobuf, use SQLite for database, and use SSH plus Unix sockets to forward, because that will be the quickest, I think, approach to get to a prototype that we can target for a feasible LTS version.
Cool. And I think there's an interesting point there, and you touched on it briefly, which is in an open source community like ours, it isn't just necessarily a decision about the best fit for the technology. It's about being able to maintain it and people having awareness and skills in whatever is chosen, right?
Yes, absolutely. So Lua, I like it, but I don't think it will make it, because that's a skill set that you add for the community. And based on what we know right now, community has skill set and developers who know Python and Go and Java. So those are the three realistic options we have. So we'll discuss and see what we decide.
Yeah. Okay. So Pierre-Luc, I'll just read this directly. On KVM and Zen server, the VR does not have a direct access to the CloudStack management from the pod network. This is somewhat a security feature. If the VR would have to report back to CloudStack? Could it use the public-facing API endpoint of CloudStack?
I mean, it can, but I don't think we should do that, right? Virtual routers shouldn't have WAN access. Like in your home routers, your router page is not accessible from public internet, right? You have to be on the LAN. So that's where a control NIC or a link local IP sort of comes in. In the example that I showed you, the SSH tunnel to kind of forward the Unix domain socket solves that problem. That way, you don't have to expose your VR agent on a public NIC. I think that I mean, if we do that, that will piss off a lot of people.
Okay, Rohit, there are a few questions left. If you could just do those in the chat, because we're actually out of time now, ready for the next session. Last thing to say, everybody, please give Rohit a big virtual round of applause. Thank you very much, Rohit.
Thank you, Giles, and thank you, everyone.